Very good evening. It's great to see so many people here in the room. So obviously the topic, well, appeared to be of some interest, and I hope that I will be able to fill that. So I think we figured a few years ago, well, let's pick a different or a difficult topic actually to map what's underneath our feet. And the tubes and pipes and cables, they are, well, the types of tubes that you see here on this image. So the tube lines in London, but that's just really one aspect. There's a lot more in terms of, yeah, pipelines, cables, cavities, other infrastructure that we try to pull together. So before I really get into this, let's start with some literature. And there's a book called All the Light We Cannot See, and it has really nothing to do with underground infrastructure. But it's the book I read when I kind of got into this topic again about 3 or 4 years ago. And assuming that many of you won't have read it, it's a book that plays at the beginning or throughout World War II, and it's a French girl, Marie Loire, who lives in Paris with her father, who works at the Natural History Museum. And unfortunately, over the time she lives in a big apartment building in Paris, she goes blind. And the beginning of the story is really about her getting to grips with that situation and trying to find her way around the city. And her dad actually builds her a little kind of small model of the part of town they're in. And so she has a fairly tactile model that she tries to learn to perceive the reality and the location. And a couple of years later or so, she's actually capable of navigating that part of the city on her own by basically counting the gutters that she walks by. So she finds out kind of her own way to perceive geography and be able to navigate. And the reason I'm telling you about this is that there was, in a way, the first really big learning for me in related to underground. And that's basically that when it comes to the underground, we're really blind, because we can't touch anything underground unless we do an excavation. And there's, as Gavin said, limited survey technology that we can actually utilize in order to find out what's underneath our feet. And we found with a team of people, and there are perhaps 10 or 15 on the Ordnance Survey side who are involved in this piece of work, with this going into this with a mindset of we're actually blind when we're going underground. I think that's a good starting point. That's a useful mindset to go underneath and map the underground. So I think I need to point out a little bit and explain what is on the screen a little bit more, because I guess it's quite difficult to see. But you'll all be familiar with the kind of network diagram of the tube, and then on the right-hand side is Westminster Tube Station, which is, well, still probably quite illegible from wherever you're sitting. But this is how Westminster Tube Station, or the building that sits on top of it, Portcullis House, is displayed on an Ordnance Survey map today. So here's the outline of the building, and then there are these packed lines, which are basically the cores of the district line here, the tunnels, some part of the kind of ticketing hall, but not a great detail. And I guess most of you will be familiar with this location. The Jubilee line, which also runs through this station, but it's quite deep down, is not on this map. So I think what we can learn from this is that, yeah, there is some underground information in today's mapping and mapping products from Ordnance Survey, but it's a little bit patchy. Not everything is there, and it's quite general. So from the book title of the book, I then basically came up with this title here, Mapping What We Cannot See. And whilst this image is a little bit made up in that the underground infrastructure that you see here is something that a graphic designer put into it, but this should basically tell you that the reality is that, there's not only stuff above, there's a lot of stuff down below the ground, but a lot of the things that you can actually see by walking through Parliament Square that are above ground have a connection to what's underneath. So these are, well, the poles where the traffic light is, for instance, and the traffic light, well, some cable will feed it with electricity and into maybe some signaling information. There will be manhole covers. There will be other elements that actually give you quite a good hint of what is underground or what might be underground. So the structure of this is five different parts. So we've been through the first one already, which was intended to be a bit of a prologue. And I want to spend a few minutes talking about mapping and technology, assuming that you might be interested in how we can measure and survey what's underground. Then we'll talk about the Underground Asset Register, which is a project that we've been doing for the last year. And that's basically a system environment that you can utilize to find out what's underground. Then I will go back a little bit to what happened before. This is how we got there, and then talk about 3D data and information towards the end. So I'm not sure how familiar you are with Ordnance survey data. This is just a very, very quick run through. So there are kind of four, perhaps the most important data layers that we have available everywhere in the country. So this is an aerial photograph. That is the master map of Great Britain, which is in great detail. Basically, every building, every road, every fence in existence. It's a navigable network, which is a combination of roads and path, as well as addresses. So that basically every addressable object, which is either a house that you can send mail to, but it's also basically every place that a person can work. So that would include a bus shelter where somebody might go in order to change an advertising board or a telephone box. And technology to survey above ground features have changed quite a bit over the years. So I went into our imagery archive and found some interesting old photos of people in kind of old cars, in this case doing some leveling, so to measure height differences, to what all of our surveyors nowadays do. And they're basically using GPS systems, and these are GPS systems that are particularly enhanced in order to go down to an accuracy of maybe around 5 to 10 centimeters in the positions they're picking up. And this is the kit that everybody's using. So it's an antenna, it's a backpack with some technology in it and a pen top computer where they can then basically plot and map the features that they're picking up. And that has actually led to a lot of efficiency savings, where previously, kind of 20, 30, 40 years ago, we had survey teams of maybe 2 or 3 people. Now it's a fairly lonely job because you really need one person who can do it all. And we have around about 250 surveyors around the country who pick up the change in the landscape. And these changes are about 20,000 records in our database that we change on a single working day. When it comes to the accuracies, this just illustrates this. So with a standalone GPS, the one that you might have in your phone, you will be able to pick up an accuracy of maybe between 5 and 10 meters. And the more effort you put into augmenting the signal that you get from the satellite, you can drive it down to just a few centimeters. The second really important technology when it comes to mapping the above ground is aerial photography. And we operate a couple of planes, and these planes have cameras in there that look like that. So these are not quite like consumer or normal photographic cameras. So this one, for instance, has 8 different lenses and picks up panchromatic imagery, so that's black and white imagery, as well as color RGB, and each of the RGB channels has a different lens. So these are quite complex pieces of technology, but in comparison to the old technologies, which were analog cameras that produced negatives that were kind of this size, this is really quite efficient because the processing times are quite short, and within a few days or sometimes a couple of hours after the aircraft is back on the ground, we actually have direct access to the data and can process the data and extract the information from this imagery. this slide just gives you a bit of an idea about the evolution of mapping since Ordnance Survey started back in 1791. And quite difficult to see here on the left side, we did a lot of initial surveys, which we put down on paper maps, which was obviously the technology at the time. And throughout the 1800s, we basically mapped the country county by county. And then towards the end of the 1800s had a comprehensive set of maps available for every part of Great Britain. Then something quite interesting happened in the late 1930s, where a committee called the Davidson Committee made some really forward-looking decisions. And they basically decided to integrate all this county mapping, so there were different coordinate systems for every single county, into one coordinate system for the entire island of Great Britain, or in fact the entirety of the British Isles. And they also went metric at this point in time. So the decision to go metric in surveying really goes back to 1936, when this committee made that decision. Back in 1975, we then started to digitize all these analog maps. And at the time, there was a projection that it would take about 50 years to digitize all of the maps. But then technology got better and better. And we were pleased to hear that we finished in 1994. So that's, quite a significant reduction from 50 years down to just under 20. In the early 2000s, we produced what you saw on the slide before, the master map of Great Britain, which is a map that basically has topologic objects in it. So every building is an object, every piece of the road, every pavement is an object with a unique identifier in a life cycle that we manage going forward over the years. And then 2011, we went into another, in fact, technology refresh with a new data management system that allowed us to store and maintain data in 3D and basically unpick the data so that we have one single database that we can use in order to generate multiple products from it. I guess this one is quite difficult to see. So I tried to find the most interesting underground map that OS has ever done, and this was probably the best contender, which is a map of Ypres in Belgium, and it's one that we did in 1917, and really difficult to see. But all the red lines that you see here are the position of the trenches. So it has a date on it, which is the 5th of December. 1917, when those were revised. So Ordnance Survey hasn't done a great deal, I guess, of underground mapping, but that's hopefully some proof that we've done a little bit over the years at some point in our history. Another part is quite interesting because we were heavily involved in the Channel Tunnel and the surveying that established the Channel Tunnel. And I guess it's quite easy to draw a line from Folkestone, or somewhere between Folkestone and Dover, over to Coquelles or Calais on the French side. What's quite easy is to get this right in what we call in planimetry. So in the X and Y, if you look at it like this, it's quite easy to coordinate the view from Great Britain over to France, and you can actually see, as you will know, from one side to the other. What's a lot more difficult is to get the height difference correct. And the reason for that is that height is defined by gravity. And the most practical way to actually define this for every single country is to do this through the sea level. And pretty much every country has put like tide gauges into place in which they average the mean high or mean low water over quite a number of years, and then at some point just defined, and this is our 0 point, and this height point has then been transposed or transported to other parts of the country. And that means there are two completely different height systems in place in France and in Great Britain, and these had to be correlated. But luckily, that led to the success that we see here. So they did the tunnels from both sides and actually met in the middle. Now, I think we have to acknowledge that they are actually specialists of working in the underground, right? They are called geologists and have done this for a few hundred years. And we've worked quite heavily with the British Geological Survey on this, and that's perhaps the second learning point, in that there are people who know an awful lot about navigating in the space that you can't really go to. And this is just a very simple example of, well, what is essentially a model of what might be below the ground. So yes, they use some techniques in order to kind of some sensing techniques to find out what's underground. But the most important method is that they will be boreholes where they basically look what's there, and then they interpolate in one way or another and create models of the underground. And there's a really interesting saying in the geological domain, which is basically saying that all models are wrong. Kind of, you can never get it exactly right, but some models are useful. And this usefulness is really a reflection of your use case and what you want to do and how you use the data or the resulting model. So that's another important mindset that is worth keeping in mind. So I think I will quickly scroll through the different survey technologies that can be utilized, particularly when it comes down to structures underground that you can't get into. So that are basically utilities that are packed into the earth. So the first one is a method that's called vibroacoustic, and that basically means you put some kind of vibrating device onto a pipe, and you would open the cover, basically put it on, and then the vibration would then go underground, and you will be able to pick them up on the surface. That works better with a particular kind of water pipes. It doesn't work particularly well with more modern plastic ones. Second one is called electromagnetic location, or this is something that people actually, this is quite widespread, particularly when it comes to figuring out where underground electricity cables go. And I think you can all appreciate that some of them, or all of them, are a little bit dangerous, and some of them could be really, really dangerous. The high voltage ones, which particularly in central London, have to be under the ground because there simply is no space to put them up onto a pylon. And that works in a way that you put a current onto a cable, and you don't have to have a physical connection to that. You can just put it, if you know there's a cable coming out of a cabinet or a substation, you put a kit onto this, and then with this device you can basically trace it and figure out where it goes. So that's a very useful technique. You can put sondes into pipes, and then you have some piece of kit above the ground that picks up where the sonde goes underneath. And then lastly, there's ground penetrating radar. So there are these kits with devices that look a little bit like lawnmowers, right? So if you see somebody in a hard hat and a reflective vest pushing a lawnmower over concrete, that's most likely not a lawnmower. That's with some likelihood some kind of ground penetrating radar kit. And then you can combine these into kind of clusters, so you can create what's called a multi-array system. And if you put even more together, you can basically put them or hook them up to a car and drag them behind you. So these are reasonably expensive pieces of kit. And some of the organizations that we have a collaboration with calculated that the actual survey effort is manageable. It's reasonably low, so it takes about 2 hours per lane kilometer. Yeah, so if you have a 4-lane road, you obviously have to multiply this by 4. But then it takes about 20 hours to process the data, and that's quite a lot of effort. And I believe the 20 hours not just a machine doing number crunching. It's machine doing number crunching plus an operator who needs to do something and needs to input into this. And we had a look at these technologies, but what you basically pick up with these pieces of kit is a signal. So a radar signal goes down, it's reflected, and you pick it up and measure it, which means you get a signal that tells you, well, there might be something underneath. And then out of this really complicated, or a visualization of this, this signal, you can interpret of what you might find there. What you definitely won't find out is who does the asset belong to, when was it laid, all this kind of attribution. You basically figure out there's something there, and with a bit of experience and perhaps reference data, you might be able to figure out how deep it is and whether it's a pipe, whether it's a small pipe, a big pipe, or a cable. So this is very useful technology, particularly if you are in a very dense inner city environment and you need to dig a hole and really want to know what's underneath. The deployment of a kit like this is actually quite useful, but we currently think it's not really that well suited to remap an entire city, let alone an entire country. So the next one is a video that we did a few years ago. So this is a project we did in a different country, in this case in Bahrain, where we integrated a lot of above ground data and all the utility data in one quite small and compact part of town where all of this data happened to be available. So we created the above ground 3D city models, and we're now going down below to actually see the underground utility networks. So what you see here is the data is quite nicely stacked up on top of each other. And what that means is that the depth of the individual utility pipes and cables, that's actually fairly made up. And the reason is that we didn't have the information about the depth, because it wasn't recorded in the source data set. But this kind of shows, in a way, it's the vision of where we want to go, that we have integrated above ground and below ground data to represent really the complexity of the city in terms of its energy or infrastructure networks. So keeping this in mind, this is not really what we've implemented in the UK, but I think it still serves as a useful vision of where things could go at some point in the future. So this is Air New Zealand, and something interesting happened in New Zealand a few years ago when there was a digger, and that digger hit a pipeline, and with that, I think it was the main fuel line going into Auckland and Auckland Airport, and it's basically halted not all the flights out of the airport, but quite a lot of the capacity. And it didn't take much. It really took one digger digging a hole at the wrong location that had a massive economic impact, which was estimated to be in the order of 400 to 500 New Zealand dollars at the time. So that gives you an example of how critical underground infrastructure, underground utility infrastructure can be. So what have we done in this country? So this really is a situation in front of my house in November last year. So I almost fell into this hole, and I'm not sure why I didn't pick this up the night before when I came back home, but SGN did a gas mains replacement. So the yellow plastic tubing that you see here, that's a new gas line, and they basically put this inside of the cast iron pipe that was laid when the estate was built in around 1950. And gas mains have a useful life of something in the order of 50, 60, maybe 70 years. So it was about time to replace the assets. So what I didn't quite understand was that every other house had a very, very small excavation in front of their building, and it was really just the point where very difficult to see it somewhere up here, where the joint was, where the house connection kind of was going into the house, that they needed to excavate and basically fix this connection and make that work. But the entire kind of 5 or 6 meters in front of my house was dug up, and there were two signs that for some reason wasn't in front of one of the other houses. One said, "Don't smoke," and the other one was deep excavation. So we needed to be a little bit careful. So I guess you've seen things like this before, right? Markers that tell you something about that there's a cover and there's maybe a valve underneath. So there is useful information in the above ground about what might be underneath. But if you look into how utility crews, the crews that actually do these replacement works and the emergency works, for instance, if you have a gas leak or water main is broken, this is currently how they do it. They have either paper maps or it can be PDF maps where every single type of utility, so that's in this case, this is fresh water, electricity, sewage, and I think gas on this side. There are 4 different maps. And these maps are produced in individual map packs that are assembled before the utility crew goes out to the site and before they dig a hole. And there's health and safety regulation in place, which says that you're not allowed to dig a hole without having your map pack. So that means if for some reason there's an error in this, or if you just need to dig somewhere here and you didn't know that when you were in the office and kind of you try to find out where the leak was and it's just off the map, what typically happens is somebody has to go back into the office, assemble the new map, and then the entire crew kind of waits outside and can't do any work, which is not a very efficient way of conducting that business and using the crew. The other way the data is mapped is that people from various different utilities come out and basically spray paint on the tarmac where the utilities are supposed to be, and that gives you an indication of where you might want to dig in this scenario. So I think that the fact that we don't really have good, reliable, and easily accessible information coming together, particularly for utility crews, is a problem that has been acknowledged for quite some time. And it feels like every few years people get together and say, well, this is really a problem that we need to do something about. And then they discuss it and figure out, well, it's all too difficult, or come up with an excuse that the data quality might not be good enough, and it kind of dies again. And that happened perhaps 3 or 4 times over the last 10, 15, 20 years. So there's no guarantee, of course, that the current approach is going to succeed, but I think we are in the best possible starting position to really make it work this time. And what we've been doing over the last year is a project that's spearheaded by a fairly new government entity, which is called the Geospatial Commission out of Cabinet Office. And they are tasked to create value from geospatial data. That's kind of roughly what they're there for. And both Ordnance Survey and the Greater London Authority through the Mayor's Office are working with the Geospatial Commission in 2 pilot areas. One is 6 boroughs in London, the other one is in the northeast of England, to pilot the integration of data in order to give better information to utility crews so that they can dig holes in a safer way and are more efficient. So as far as the London pilot area is concerned, so we have 6 boroughs from the city, Camden, down to Croydon, quite a number of utility operators, so that's basically everybody who's operating in this area, as well as local authorities themselves. And we think it's quite important to actually have local authorities on board, A, because they are asset owners themselves, so local authorities typically operate things like street lighting, they might have their own communications network, they might have their own electricity networks, but they also have other very useful information about sites of special scientific interest, for instance, or tree preservation orders. So if you have a particular tree that you can't really touch or shouldn't compromise, the tree obviously has roots, and that has an impact on digging holes in the ground. And then we have the second area, which is roughly from Middlesbrough to the Scottish border with Newcastle, Sunderland in the middle, and again quite a number of local authorities and utility providers. So the problem space is in a way that you would hope that all the cables are kind of nicely next to each other like this, but quite often it looks like this when you open the grounds. And from an information management perspective, that's basically a big interoperability issue. So you have data in pockets with all the utility providers who have, to some degree, knowledge about their assets. For some organizations better, for others it's perhaps not so good. And in our approach, what we're basically saying is that we don't want to resurvey everything. We want to bring together the information that's already in existence and then drive up the quality and the completeness of this information over time. That's kind of the general idea. So there's a little bit of a photo competition between the people who are involved in the project, and this is our favorite photo, which was on social media just before Christmas, where somebody put some kind of drill in the ground and nicely swirled up all sorts of cables, which I think are largely telecommunication cables. So I think you can read this as, well, no broadband access for a lot of people in the in the neighborhood for a little while. And what we've now made available to guys like him is a system which would run on a laptop or a Toughbook or a mobile phone, where you can basically go in and say, this is my location, draw a geometry like a circle, which you can quite easily do by clicking on kind of the center point and then giving the radius, and then it pulls together information about all the underground utilities in this area from the variety of different providers. This is some functionality that we started to roll out a couple of months ago with the participating utilities and local authority, both in London and the Northeast. And the feedback that we've been getting from the operatives, from the engineers, more or less, well, can I have this tomorrow, please? We are currently a little bit hesitant to allowing kind of full operational use. And that is basically because of health and safety regulations, because we don't want to create the situation where there's a regulation within an organization based on these old map packs, and for some reason they say something different than what we provide in the system. And we don't want that ambiguity from a legal perspective, at least at this stage of the project. But pretty much everybody we talked to said this will make my life a lot easier. This will be a massive improvement to my job from a health and safety perspective and from an efficiency perspective. So to go into a bit more detail, once you click onto one of these assets, you're presented with a actually quite short list of attribution and further information. And we would have a lot more data about particular assets, but there's an agreement between the different utility providers that it's perhaps not that useful to actually portray everything. And kind of the ease of use of a system like this basically means that it's probably a lot better if we don't overload people with information, give them just exactly what they need in order to do the job, and present this in the same way for every single utility type, and ideally in the same way everywhere across the country. So this is a sewer pipe. It belongs to Northumbrian Water. It has a flow type of gravity, so it's a gravity sewer. It's made out of concrete. It has a diameter. Difficult to see here. There's some metadata about when the data was surveyed or verified in the field, when it got into the database. There's a telephone number in case, well, something goes wrong or you need more information. And there's the identifier in the asset owner system. So that basically allows you to then have a conversation with whoever is on the other end of the phone line to identify exactly which asset you're talking about. So in terms of the quality, there's a British standard called PAS 128, which suggests this this hierarchy of 4 different quality or verification types. And the best one on the right-hand side is type A, which is basically saying, well, you dug a hole, you checked, it's there, and you surveyed it to a great level of accuracy. The second one is the type of techniques that we saw before, the underground detection techniques. C is site reconnaissance, so that is basically looking at the above ground evidence for what might be underneath. And type D is to just rely on the data that the utilities hold. And the idea is that we would start with type D and then put additional information into it to kind of graduate it to the system and make the accuracy of the data better as we go along over time. So you see this small circle here, and in the middle it says 9677 square meters. So one of the mechanisms that we have is that we don't want to allow people access to all of the data. And when you dig a hole, you probably don't need data for the whole of London, right? You need it for your street corner or maybe the street that you're digging up, and that's basically it. So for this particular user type, there's a restriction to 10,000 square meters, and if you draw a circle that's larger, it all goes red, and it wouldn't allow you to retrieve the data and basically snaps back to the smaller geometry. There is currently a system in Scotland who operate the integration of underground utilities, so that they have been doing this for the last 10 years, where everybody has access to everything. And while that on one level is quite nice, we don't think that's really scalable, and we think there are some quite dangerous security implication, at least in some areas. And keep in mind that the City of London is one of our test areas. So the decision to actually restrict data access to what people need is a very important principle and design principle of the system. Whether we've gotten this exactly right with the 10,000 square meters, whether we want to have other roles in the system that have a different amount of access, that's still to be decided. The way we tried, or where we think we can actually improve data quality over time, and generally data quality for underground utility assets range from somewhat usable to completely mediocre, is that we would allow observations on the existing data in the system. So if you dug a hole and basically figured out that a utility wasn't there where the map indicates it should be, you can put a very quick observation into it to say, it's not here. You take a photo and it goes back to the asset owner, and then the asset owner has the opportunity to improve the data. Electricity data sets often come with these kind of cross sections. So UKPN, UK Power Networks, who is the operator in London, has 10,000s of these in the 6 boroughs that we worked in so far. So if you extrapolate this to a larger area, you really come up with millions of these cross sections, and they're quite easily accessible. There's a cross section marker in the system. You click onto it, and the cross section comes up, so you can see how it looks like. Some of the data, particularly in London, hasn't necessarily been digitized. So it has been scanned, and it's available as kind of scanned maps, and we integrated these scanned maps into the system as well. So there are areas in London where some of the data is in scans. There are some boroughs where this isn't the case. In the Northeast, luckily, we all have web vector data, so there's no need for scanned maps. This is a very high-level architecture diagram of the data hub that we built, and the users and consumers of the data are here on the bottom, and the source data sets are on the top. And we allow data to be fed into the system in 2 different ways. So we implemented a central database in which we periodically load and upload and replicate the data sets that have been produced by the utilities. But there's another mechanism where we have an API connection where we just channel data through in real time, so that the user makes a query and it's channeled through in real time. And we figure that this is important because some of the utility providers want to have a bit more control over the data and what they make available, while for others it's just a lot more convenient if they don't have to worry about the data management and data provision within their own organization. So we kind of take this off them. We work quite a bit on the cartography. So you see there's a color palette and the colors that we've chosen to represent the different utility types. think I go through this. Data harmonization is quite an interesting one. So there are about 700 asset owners in this country. That's our estimate. And of course, everybody does things in a slightly different way, right? So at the end of the day, they're all cables and pipes, if you like. But everybody has a slightly different data model approach and the way the data is represented. And we felt that from a usability perspective, it's really required that the data is harmonized so it would look very similar for all the different utility types, and it would look very similar wherever you go into the country. And in order to make that happen, we worked with an organization that Ordnance Survey does a lot of work with, which is called the Open Geospatial Consortium, which is a standards body in the geospatial field, to look at or to utilize a data model they have developed for underground utilities, and we developed a particular profile, a particular subset for the use in this project. And that basically means that whilst we are currently focused on safe digging and associated planning efficiencies as a use case, this data model called MUDDI, which stands for Model for Underground Data Definition and Integration, has a lot more capability, which means we can then once we go into additional use cases, can basically copy across or borrow from the concepts that are already in existence. I don't know whether you like things like this. So a lot of UML modeling went on. If you like angle brackets, there's a XSD schema for the data. So some of you might like it, some of you don't. I don't know. There's an advisory group of the project, and the reason that I'm quickly wanted to talk about this is that there are some other geographies. There's Scotland. There are a number of other European countries where systems like this are in operation quite successfully, and we try to dip into their experience. There are academics in this, so a lot of effort actually has been going into research for the last 15 to 20 years. One particular example is the CLIP system in Flanders in Belgium, which is more a request-based system. So it basically says you make a request, and that is then farmed out to the variety of utility owners in a particular area. And then it can take up to 2 weeks to get an answer back. What we're trying to do is really a real-time response where somebody out in the field can query a data repository in real time. Project Iceberg is an initiative by the Future Cities Catapult, Ordnance Survey, and the British Geological Survey that looked at the value of land and the relationship to underground. And we've identified a number of additional use cases that we could go into at a later point in time. But we feel it's actually quite important that we don't widen the use case too early, because we really want to make a system for larger area work before we widen the use case. And that was quite critical user feedback we got at the very beginning. So how we got there, I think I stepped through a number of these slides. So in 2018, we worked with a particular utility, Northumbrian Water Group, and they do an innovation festival every year. And the challenge that we set ourselves is to say, well, can we actually pull all this data together and create this underground map within 5 days? And the way this innovation festival works is they create a tent city and then have 13 different development sprints over a course of 5 days. And this is what our tent looked like. So we had 50 to 60 people in this tent every single day throughout the week. And at the beginning of the week, we had some talks from people who have implemented similar systems in other countries to look what might be possible, to actually pulling together the data by the end of the week and make it available through APIs to a number of target GIS system, geographic information systems. What was quite important is that we actually started the week by digging a hole. We figured that was really, really essential because most of the people in that tent had probably never dug a hole before in their life, or at least not one that was close to underground utilities. And what was really useful and good to see is how the engineers who are doing this on a daily basis, A, how are they going about it, and B, what information needs do they actually have, and how do they use the plans that they currently have access to. So the outcome of a festival was kind of a first prototype system, which kind of the circle you might recognize. It looks a little bit like what I showed you before. But in order to get all the utility providers on board, we basically said to them, give us your data, give us just a little bit of your data, and rest assured we will delete it by Friday 5 o'clock. And that was a big problem, because at the end of the week, everybody wanted to continue. So that meant we had to stand down the system and then create kind of a new structure, new legal framework around it to bring it back up. And that took us a little while to do. And then half a year later, the Geospatial Commission came on board, and we created what you just saw. So the very last part is about, what about 3D? It's a question that we usually get. And the reason that we haven't really approached this from a 3D perspective is mainly that depth information doesn't exist in the input data. You have it for sewerage, which is gravity fed, so it's kind of a must. We know that telcos are roughly like 30 centimeters around below the ground, and the others are kind of stacked below that. But it's simply information that is not there. There is a lot of stuff that's technically possible. Kind of there are data models and implementation where you can particularly transport networks representing great detail in 3D. But I guess this is something for the future. You might have seen, well, I guess some advertisements about nice little AR kits where you can hold up a phone or a tablet and then have this radar view of what's underneath. I tried it a couple of times. I don't think that the user experience is as good as this image kind of promises. It's not completely bad either. But I think what I wanted to say is that the focus that we're really trying to put onto is on interoperability and bringing data together and actually producing something that's quite easy to use and fit for purpose for the engineer in the field. Yeah, so with that, this is the idea. Give ready access to this to this kind of information, and we hope that we will be able to roll this system out to a larger regional and hopefully national level at some point over the next few years. Thank you.